Morning, everyone. So yesterday we started looking at the equilibrium expression. I'm just going to start you off with a quick warm-up question just to see if there was any questions. We will do a lot more with the stressing and the shifting of equilibrium. Does it go towards the left or the right? A lot more in this lesson, but at least I want you to be comfortable with writing this Kc expression. So let's say, just as an example here, we're going to start off with 2SO2 as a gas. This is in equilibrium with oxygen as a gas. In equilibrium with 2SO3 as a gas. Right. So a couple of notes here. Even though I know we've hit equilibrium, that's why we have the symbol here, we still read things left to right. So we still call these ones here reactants on the left, products on the right side. We're going to start off, can you write for me the equilibrium expression? If I did Kc for this equation, what would it look like? So Kc, if you remember from our derivation yesterday, Kc is essentially always going to be the concentration of reactants divided by concentration of products. Somewhere behind the scenes, the Kc actually dealt with the rate constants ratio, and therefore, because it was a sort of K forward divided by K reverse here, this one here, it only depends on temperature. That's something we're going to see a little bit in this lesson. All right, but we're going to use big K just to make sure we're clear here. So it's just K forward divided by K reverse. And basically, you do the product over reactant ratio with this expression. So products, in this case here, I would know I'm going to ignore any solids or pure liquids because all of these three are gases, so I'm going to include all of them. I'm going to take the SO3 and square it, divided by the SO2 and square it. Remember, we get the powers here directly from the coefficients. We couldn't do that in our kinetics chapter because our order of reaction doesn't follow the coefficients nicely. I don't know the mechanism, but in this chapter here, yes, you can make sure the equation is balanced. You can just treat those as powers directly. Right? So what does this Kc imply first? Remember, Kc in general, it's saying products or reactants. If I'm at a temperature where the Kc, my constant at this temperature, is much bigger than 1, that just tells you I have more products. I have a ton of SO3. If my Kc is less than 1, yes, bounded by 0, we know we have more reactants. That's all that this ratio tells you, right? So it tells you even though we've hit this balance, even though we're at equilibrium, forward is becoming products, and then products are becoming reactants here, it tells you at this particular temperature, do we have predominantly reactants or products? We saw a little bit of this Chatellier's principle yesterday. We're going to do a lot more of it today. But basically it says here, naturally, systems will approach equilibrium. Right? So you don't have to force it to happen. So 2 lessons ago, we started it when we introduced equilibrium. We said we could start off with pure reactants or pure products. Let's imagine we started off, so as an example again, let's start with pure reactants, only reactants in the container. In this case here, well, I'm going to call it Q instead of KEQ because I know I'm not in equilibrium yet. I can't be in equilibrium if I just have the one side. Q is essentially this Kc. It's essentially this product of reactants. And right now, if I start off with pure reactants, I have a ton of reactants and basically 0 products. Well, what's my Q value right now? My Q value currently, 0 divided by anything, is just 0. Let's say for argument's sake here, the K was supposed to be 10 at this temperature. Well, obviously, my number is not large enough. So as I try to get towards equilibrium, since my Q value is currently too tiny for what it is to be Kc, what I end up needing to do is I need to, for some of these reactants, I need to produce some products. As I gain my products, my numerator goes up, my reactant number drops, my 0 is going to steadily climb from 0 up to 10. So in this case here, we can say the equilibrium, we actually need to shift right, or we need to go towards the products to end up hitting equilibrium. What if we had the opposite? What if we started with just pure products? Products only, right? Let's assume we're at the same temperature, so the K is supposed to be 10 at this temperature. Well, if I have products only, again, just a little bit of hand-wavy math here, Q is this test KQ value. It's this ratio when I'm not guaranteed I'm in equilibrium. We have a ton of products. This is some number. And the reactance is essentially 0. I know I can't divide by 0. But if I divide by a number that's 0 or something close to 0 here, the Q value is very large. So maybe my Q is like 3,000, right? But it's only supposed to be 10. So what happened in that case there is, since in this situation, the Q is actually too big for Kc, my test product over reactant ratio here, the fraction itself has to shrink. For this one here to shrink, I need to lose products and gain reactants, looking at which side these are on, to actually lose products, I need to force my currently all products, I need to force a lot of them to become reactants. As I steadily pick up reactants, my denominator increases. That's going to take down this very large Q, and it's going to get closer and closer to this 10. We basically use this comparison to figure out, I'm supposed to be 10 by the time I hit equilibrium. Do I need to shift right or shift left? In this case here, it needs to shift left. In fact, here, I'm not going to do it all the math with you currently, but if you imagine here, if I gave you the concentrations, if I gave you SO3 is 0.1 molar, 0.2 molar, 0.3 molar for the O2 here, you can actually calculate what the Kc is at this unique temperature. As long as the temperature is not changed, the Kc will always be this 10. If you then come along, yesterday we sort of alluded to it, oh, let's double the oxygen, or let's half the SO2, whatever. If I come along and start changing some of these numbers, we would temporarily be out of equilibrium. My Q would not be the same as K. It's either going to shift right or shift left, as you just mentioned. And basically, mathematically, I would know the Kc, I would know a bunch of these numbers here, what is it right now, and I can actually figure out by the time you reach equilibrium again, what maybe an unknown would be. So that's sort of the direction that we're heading towards the end of this chapter here. In today's lesson, I just want to recap with you some of the Chateliers, just to figure out a little bit of the shifting stuff here. You don't need to memorize this stuff. That's an important note here. You should be able to study the equilibrium as given to you. So let's start off here. You can flip over into the page, Le Chatelier's principle here. For Le Chatelier's principle, one conclusion that we said already was, if I have a system that's currently not in equilibrium, if I have just reactants, just products, or even a mixture, but it's not at equilibrium, systems naturally go towards equilibrium, right? However, what if a system is at equilibrium? What can you do to the system? So what's going to happen in this situation is the equilibrium is already happy the way it is. The reactants are becoming products as products are becoming reactants. Remember, the concentrations are constant in time. So these are some notes that I want to keep reiterating for you here. Concentrations are constant in time, right? But the concentration of reactants does not have to equal concentration of products, right? So we already hit this equilibrium. What the Chatelier's principle does for us here is it says, what if I poke this equilibrium? What if I take this equilibrium system, I subject it to a change? I'm going to refer to that part there as a stress. I stress out the system somehow. I increase the temperature. I pull down the concentration. I add a catalyst. I poke at the equilibrium somehow. What the Chatelier's principle tells me is it tells me the direction that the system responds is that it tries to go against your change. It tries to counteract your change. And I want to add this phrase here. System will try or tend to. We're going to see in these examples here, it never really gets rid of the change completely, but at least it's going to try. All right? So what we're going to do in this lesson here is we're going to see what are some ways I can poke the system, and then we're going to see how the equilibrium actually shifts to respond. It's not that the chemicals have a mind of their own. They could be like, oh, you did this, I want to shift this way. We're going to try to analyze how does the system respond in this fashion. And how we're going to do this here is we're going to identify what's the stress, and we're going to try to see what the shift of the equilibrium is going to be, what's the response upon doing that stress there. All right? So let's just start off here. We have an equilibrium system here. We have to already be in equilibrium. If we're not in equilibrium yet, don't do Le Chatelier's principle. So I'm assuming we are already currently in equilibrium, and now what I'm going to do is I'm going to poke at the system somehow. All right? My stress, what I decide to do, I could have chosen any of these chemicals here. I decide to add some N2. Right? So in my container, wherever we are, I decide to pump in more N2. Now the equilibrium was already happy the way it was. It doesn't like that. So what's going to happen here is the response, the shift from the equilibrium, the shift is going to try to remove the N2. So the shift, we're actually going to shift towards the products to consume some of that extra N2. How did I know it was towards products? One easy way of doing it here is we have the equilibrium system, right? It's written in this fashion. My stress was I increased N2. I pulled this concentration way up. Nature doesn't like that. Nature wants to get rid of some of this N2. Nature can choose, right? It's stuck in the box. It can either shift to the left, that would take ammonia that would generate even extra N2, or, like we said, it can shift towards the product. It can sort of push away from how I poked it. It's going to shift towards product so that all the extra N2 is going to collide with H2 and then going to end up becoming NH3. So it shifts towards products. It's going to try to consume the N2, and basically what's going to happen, we can actually plot this out graphically here. I don't know what the initial amounts is. Okay, although we don't know the relative amounts, right? They haven't given me enough information. They didn't tell me, even before you poke the equilibrium, do you have more NH3? They didn't tell you any of that. Let's just pretend. So I have NH3, there's that concentration here. I have my N2, and I have my H2. I don't know these starting amounts here. I don't know exactly what numbers these should begin with. But what I can track is by poking the system, I can track what the overall change would look like. So currently here, you'll notice that these lines here, I'm plotting the concentration against time again. Remember we had said equilibrium is supposed to be constant time here. Whenever these lines are flat on a time graph here, we know we're currently at equilibrium. What we usually do on these graphs here is I decide at one moment t1, I decide to do the stress. I decide to poke the equilibrium. In this case here, by poking the equilibrium, I added a bunch of N2 all at once. Okay, so the N2 concentration goes way up. The other two have no idea just yet. What's going to happen over time is the system doesn't like that. The system wants to shift towards product, use up some of that extra N2. As we shift towards product, it's going to try to pull this concentration back downwards. So the N2 is going to steadily drop, fine. Poor old hydrogen was minding its own business. It was actually on the reactant side. As I shift towards the right, I'm also going to have to lose hydrogen. So I'm going to lose hydrogen. In fact, if you did this by mole ratio here, look at the mole ratio is 1 to 3 ratio. This ratio that the hydrogen drops by is actually 3 times as big as the N2. These lines here can cross each other, no problem, but at least I can see that ratio there. My stress was only adding N2, but as the equilibrium is responding and going towards the right side, it ends up creating more NH3 as a mole ratio of 2, so this NH3 line is going to steadily go up, but it's going to take a little while to climb, so that's why it's going to be a gradual change. All right? So in this case here, a couple of notes. We have a sudden change, so a sudden increase in N2, and I could have stressed out by adding any different chemical. In this case here, I just did the N2. The other ones here are much more gradual changes. Gradual changes as the equilibrium responds, as the equilibrium shifts. And what I want to show you here is we can make a conclusion. The graph actually says it all. Well, after it's shifted, what's happened to the concentration of NH3? Well, the NH3 used to be some number I didn't know. Based on me shifting towards product and creating more of it, the NH3 has increased. Right? What happened to the hydrogen? The hydrogen here was only minding its own business, but unfortunately it's on the reactant side here. As I end up shifting towards the right, the N2 eats away some of that hydrogen. The N2 has decreased. The hard one is going to be the N2. The N2, a couple things happened to it. The N2 at first, it was minding its own business, it was at equilibrium. During the stress, I poked at it, I increased it way up. As I increase its own way up, equilibrium responds and says, I don't like that. I want to pull that down by shifting to the right. I want to use up some of that N2. That's why we saw this N2 here dropping. But here's this notion here. Equilibrium, although it's going to try to counteract you, the key hint here is it tries. It never gets you back down to what it was initially. Initially, the N2, let's say it was 2 molar here. Maybe I increased it to 5 molar. I might be able to bring it downwards, but it's not going to be down to that 2 molar again. Usually when they say, well, what happened to the N2? Lots of things happen, right? It went up, it's going to come down. But usually they use this phrasing here, compared to the initial equilibrium. Compared to the really, really beginning, what happened to the N2? Overall, I'm going to say the N2 has increased. And then you're going to say, well, wait a second. I thought during the shift it was actually decreasing. You're totally right. It's increased during the stress. It was dropping as it was shifting. But what I'm saying is by the end of it, I'm actually higher than where I started. This one here, maybe it's easier to understand here. It's more than the start. It's not increasing during the shift. I'm actually trying to get rid of it, right? It's trying to go against you. But overall, compared to the really, really beginning, it's actually more than before. So there's a conclusion for concentration changes here. I just did one particular chemical. Equilibrium tend to shift away addition. I want to point towards the other side to get rid of it. And if I remove it, let's do the contrast here. What if I took the system and I took the H2 and I pumped out the hydrogen? Again, nature doesn't like the fact that it suddenly lost a bunch of hydrogen. It's going to shift towards it. It's going to preference the reverse reaction in that case there to try to regenerate the hydrogen, although it's never going to really make it back up to what it should have been at the beginning. So we're going to shift away any additions. We're going to shift towards any removals. I want to maintain this sort of balance. I don't want to have suddenly increase one chemical or suddenly have decreased another chemical here. Again, I want to imply here, remember, it's not like the system has a brain of its own and it's sort of like, oh, I'm going to shift left or I'm going to shift right. How does the system know to do this? So what I'm going to do here is just a quick aside here. Usually for this aside here, if they ask you this phrase here, can you explain this shift? Explain how we responded. Explain shift in terms of rates. That's when you need to do this aside here. And here's what's going to happen. We're going to plot a graph because it's the easiest way to do this here. We already started seeing this graph here. I'm going to plot the rate versus time. At the beginning, before T1, these rates here had to be equal. So let's just say here our forward rate in red, our forward rate, and our reverse rate in green. These two lines here have to be equal to indicate that we're starting off. This is our initial equilibrium. The microscopic reactions continue to occur, reactants become products become reactants, but the rates equal one another. Remember, in this situation here, my stress was I suddenly added more N2. Okay? So what does the forward rate depend on? The forward rate depends on N2 and H2. Right? These have to collide with good energy, good geometry. What I've done during my stress is I've suddenly increased the N2. I've suddenly increased way more N2s. So therefore, there's going to be a lot more collisions. The chances of you having a good energetic collision, good geometry and all that increases. So the forward rate, which depends on the N2, H2, upon adding the N2, the forward rate increases. So forward rate goes up. There's more chances of a better collision. How about the reverse rate? The reverse rate also depends on, well, in this case here, the products. It depends on the amount of NH3. The reverse rate, which depends on the NH3, does it actually care that there's more N2? For starters, no. For starters, ammonia just needs to collide with itself. It needs to break up and decompose between N2 and H2. It could care less that there's extra N2s around, right? It's already gas. It's already spread out through the container. The reverse rate at the very beginning doesn't really care. And that's what we actually have. Upon doing this stress, upon adding the N2, I have actually increased the forward rate, but I haven't changed the reverse rate. Anytime this happens, right, the rates are not equal because the forward rate is bigger than the reverse rate. The equilibrium shifts right. Imagine we had a situation of balance, right? The forward is going, the reverse is going, but they end up having after you did the stress, suddenly the forward rate is predominant. It's more than the reverse reaction. Therefore, the equilibrium will overall have a net increase of your products. But over time, what's going to happen? Over time, as the N2 drops, as the H2 starts getting consumed, we start losing these particles here. There's not as many particles to collide anymore. The forward rate here does end up leveling off and start dropping off a bit here. The reverse rate, which initially didn't care, initially it only depends on the NH3. Well, as you predominantly favor making more NH3, over time you're going to make more NH3, more NH3, more NH3. And as you get more NH3, this one here will start climbing. Eventually you're going to hit a situation where, again, the forward rate is equal to reverse rate. We've hit an equilibrium again. The rates are different from before, but we do know we're in equilibrium because the rates are equal to one another. All right? So we're going to actually reach sort of a new equilibrium here. You can say here, a new equilibrium than before. Right. I actually have a situation that I actually have more N2 and less H2 and more NH3 than before. New equilibrium with the same Kc ratio. Because this was just a concentration change, even though all three numbers have changed, somehow they preserve the Kc. The Kc equilibrium constant only depends on the rate constants. Right? Okay. Secondly here, let's look at the next thing I can poke at the system here. Temperature is my factor. I need to decide whether I'm going to increase or decrease the temperature. So let me just rewrite our equation here. Rewrite it in exactly the same sort of ordering that they have it. So reactants are the N2 and the H2. This one here, I will need to worry about the heat term. We alluded to this yesterday. Let's say what I come to do, how do I poke the system? I stress it out by decreasing temperature. Right? So what I do is I take the whole container that all these gases are in. Remember, we are already at equilibrium when I poke the system. I decrease the temperature. I cool down the entire box. How does nature respond? Nature doesn't like the fact that it's suddenly cold. It then tries to generate and recreate some of this heat. Nature is stuck in this box here. It can either try to go forwards. That's an exothermic reaction that's going to regenerate some heat, or it's going to try to go in reverse. The NH3 is going to take even like more of that heat here that I'm already lacking, and it's going to absorb it to go into H2. Which one here will actually increase the temperature for me? In this case here, our nature's response, we want to shift towards products to regain some heat. Does that mean nature really likes things hot? No, it just doesn't like the fact that we've actually cooled it down. If I heat it up, nature's going to try to cool it down. Nature is just always fighting me. And how you can see this here, just like we did with the concentration, and we did this sort of conclusion, shift away, shift towards like that, even though I'm cooling down the entire box, I'm just going to focus on this energy term. If I focus on this energy term, as I cool down the box, it's like I pull away energy from the system. Nature doesn't like that. When I did this removal, the equilibrium is going to shift towards that removal. It's going to try to exothermically release some heat again so that I can heat up the box. Again, it never gets it back up to what it was at the really, really beginning, but at least it'll help. So in that case there, we already said it shifts right. We can do our conclusions here. What happens to the N2 and the H2? Well, as nature tries to shift it to the right, I need to use up reactants. Sure, I'm just focusing on the heat that's generating, but the N2 actually needs to, these guys have to collide, good energy, good geometry. These guys actually drop, and the NH3, which is the only product that we have, the NH3 actually increases because I've shifted to the right. I've created more and more and more of this NH3 here, right? So again, I can show this graphically speaking here. Again, I don't know the starting amounts here. Let's say for argument's sake here, I start off with N2 as high on the side, maybe ammonia in the middle just to confuse you here. Let's do hydrogen. I don't know the relative amounts because they didn't give me that information. I know for starters, we have to be in equilibrium. We don't do Le Chatelier until we're at equilibrium. At T1, what we decide to do is we decide to cool down the entire container. Because this is plotting concentration changes here, it takes a little while to actually cool down. It's going to take a little while for these concentrations to actually respond. It's not going to be a sudden jump. So what's going to happen here is, upon cooling down the system, upon shifting to the right, the N2 and the H2 are going to drop. The N2 is going to start falling. Right? It's going to fall with this sort of 1 to 3 ratio. It's relative to the hydrogen here. It's never going to drop to 0 because remember, even at equilibrium, we need to have all reactions and products present. That way the two rates can equal one another. But there's the 1 and the 3. And then we have ammonia, which is a product. It just is sort of by consequence here, as you exothermically release that energy, we actually do create more ammonia. The NH3 here does climb. These lines here can totally cross each other, no problem. It depends on what your starting amounts are. So therefore, for a temperature change, we see gradual changes. All of them are gradual changes. There are no sudden spikes. Like earlier, we had a sudden spike in N2 because that one went way up. Notice in this case here, this one is a temperature change. So I want you to imagine with me here, we start off with that equilibrium constant. Kc is supposed to be products over reactants. Right? In this case, you just practice NH3 squared, N2 and H2 cubed. Kc is an equilibrium. Kc, let's call it Kc1, is this ammonia concentration squared divided by this N2 divided by this hydrogen cubed. Let's compare it to the new Kc. Let's compare it to the new equilibrium constant over here. The expression is exactly the same. It's still ammonia squared divided by N2 and 3H2. We are exactly the same reaction. But if you look at what's happened here is my N2 and H2 have dropped. This number went down, the hydrogen has gone down. The NH3 number has gone up. Well, if the numerator has only increased and the denominator has only decreased, my Kc is now going to be larger than before. So upon doing this decreased temperature, you can check it with the conclusion from yesterday. Because I'm shifting to make more products actually makes the Kc value actually a little bit larger. So we can write that in words here. Kc, the new equilibrium constant, the number describing this equilibrium, the new equilibrium constant is larger than before. Not only have the concentrations, the numbers, or the molarities themselves changed here, this ratio has actually changed as well. Now you might be looking earlier here, you might say, well, what about earlier? Didn't the concentrations change? You're right, it did change. The NH3 has gone up, products have went up, but you notice because there was this little bit of contrast, the hydrogen went down and the nitrogen is still higher than before. Sure, the hydrogen went down, but the nitrogen went up. Because it's not a temperature change, even though the concentrations are all different, the ratio is still preserved because the rate constants are the same. We gotta write that down in words for you here. So in comparison to this one that we just did, let's look at this situation. In this situation, although all the concentrations have changed due to my increase in N2 like we did earlier, although all the concentrations have changed, the Kc did not, because rate constants, right? That's what this Kc ratio depends on. Rate constants only change with temperature. So no doubt that all three numbers are different, right? The N2 is different, the NH3 is different, but somehow these ones here have changed in such a perfect way that the ratio has stayed preserved. Right? So there's another thing I can poke at the system here. I'm going to do another aside here using that phrasing here, explain in terms of rates. How does the system know? Oh yeah, cool it down. Oh yeah, I want to regenerate more heat. It's not like the system has a mind of its own. How does it know to shift to the right? What I want to do with you here, again, this is just an aside. This hopefully will just help explain this temperature factor a little bit more. As an aside, again, I want to just explain in terms of rates. Currently, we have an exothermic reaction. So let's plot this out here as a potential energy versus reaction axis. An exothermic reaction here has the N2 and the H2 start out a little bit higher. Exothermically, we have our 2NH3 here a little bit lower. We talked about there being an energy barrier in the last chapter, right? Even before you did this shift, which reaction is harder, right? And I mean that in the sense here, in this case here, our EA forward, you notice that red arrow. Let's compare it to the EA in reverse. The ammonia here is actually, let's do this blue arrow here, EA reverse. For starters, even before the shift, since the EA forward, since the activation barrier going forward is much smaller than EA reverse, right? That just happens for an exothermic reaction. For an exothermic reaction, I would say the forward reaction is easier than the reverse. Right? I don't need those really, really fast moving particles to actually get over the hill because the hill was not actually that big. The reverse is actually different. The reverse, it really needs to be the really lucky NH3, good energy, good geometry, or else it won't actually form that transition state activated complex. Now what have I done? I've taken this entire box and I've made the whole box colder, right? So these boxes, these chemicals here were zipping around any which way. I decided to make this entire box colder. And what's going to happen here is every single particle is going to move slower. Which one will I have affected more? Now this one here, the forward reaction here, these particles are slower. The N2 and H2 are slower. No doubt it's going to be a little bit harder for them to get over the hill. But the NH3, which actually had a hard enough situation to begin with, as those particles get slower, we have even less of them that can actually get over this energy hill. So again, let's just explain this in words here. At colder temperatures, all particles are slower, right? So they have less sufficient energy. So both rates decrease. But because we had already said the forward reaction is actually easier, I would still imagine that the forward rate, if it's going to drop, it's not going to drop by as much. The other one here, which really we were crossing our fingers, I really would need the really fast moving ones to actually get over the hill. There's really going to be not any chance for these guys here to get back over. So again, if I analyze this in terms of rate, plots this on a rate versus time graph. At first, we were at equilibrium. At first, we had forward rate and we had reverse rate, right? If we're not at equilibrium, don't even do Le Chatelier, right? So this is bearing in mind here, we already knew the reverse reaction was already harder, but we were at equilibrium. We've hit a balance, right? We're at a temperature where the concentrations stay constant in time. As I stress it out by making it colder, we know both rates are going to drop. So the forward rate is going to drop, but what we're going to see is the reverse rate actually drops a lot more steeply than the forward rate. And just like we did earlier, oh, I have a situation where my forward rate is actually bigger than the reverse rate. This is how the equilibrium actually shifts right. It's not like it has a brain of its own and be like, oh, I want to shift right to generate more heat. It's just that the forward reaction, the reactants have slowed down, but it was easier to go reactants to products anyways. Overall, it's going to have this shift towards the right. As I shift towards the right, we're going to steadily lose reactants even more. It's going to start dropping even more. I'm going to slowly replenish the NH3. As I get more NH3, even though they're really slow, they're really having a hard time going in the reverse direction. These ones here are going to steadily climb up again somehow, and then they're going to end up matching up before hitting a new equilibrium. But there was a time in here where the forward rate was bigger than the reverse rate, and that's how the equilibrium knows how to shift right. So let's just finish off on the backside here. Pressure is another thing that we can deal with here. Whenever we looked at pressure, we are only looking at gases. Gases are said to be compressible. They respond really quickly to volume and temperature or pressure changes. Remember, we had inverse relationship, so inversely related between, let's say I increase pressure and I decrease volume. So sometimes it's hard to think, well, how did I increase pressure? Because they're opposites. Think about I've suddenly squeezed this container. So let's just do as our stress here. Let's say our stress is I have increased pressure. It could have been decreased as well, but let's just do it this way. Increase pressure, because pressure and volume are opposites here. I could have done that by decreasing volume, by lowering the amount of space that we have to actually sit in. So let's imagine here we started off in a container that was really, really large, and what I've done during my shift is I've suddenly dropped the size. I've suddenly shrunken it here. Gas, in some sense here, doesn't really care because the gases were already so wildly apart here. They're already spreading out through the container, but no doubt they'd now have less room to actually move in. The shift, just for simplicity here, let's just predict the answer. The shift is going to be the equilibrium shifts towards the right to save space. Right? My stress was I took away a lot of space from you. So what's going to happen here is, how does shifting to the right actually save space? Again, the chemicals are all stuck in the container. We're a closed system. But if you imagine with me here, we actually have 4 moles of gas on the left side and only 2 moles of gas on the right side. Every time I shift towards the right, I take 4 particles worth of particles, right? 4 moles worth of gas, and basically convert 4 into 2. There's now going to be less particles that can actually spread out through the container. In that situation, when I convert 4 moles down into 2 moles, for every time that happens, I have less particles. I would inevitably have saved space. So in that case there, again, I have no clue where the N2 is, where the H2 is. I don't know the relative amounts because I didn't actually give you a temperature and actually study what the relative amounts are. But what I can do here is I can track at T1, I decide to stress out the system. I decide to poke the system. Now there's one added feature here. Because concentration, right, that's what I'm plotting on the y-axis, because concentration is moles over volume, what happens to gas concentrations as I suddenly shrink the amount of volume? At that instant, when I squeeze the entire box, the concentration goes way up. The size of the container has now decreased. It's like my molarity has increased by a lot. All the gases are going to respond. In this case here, we're going to get sudden jumps in all 3 of these here. As long as they're gases, they're going to respond just because I have, in this case here, decreased the volume. So you can make a note to yourself here. How do I know it's a concentration change? I have a sudden jump for having less room. Suddenly, when I have less room here, suddenly all the concentrations go up. Now, we are used to, if something, let's say, for example, if something has gone up, it wants to shift by going downwards, right? That will be on one side, but we're going to see what happens here. As I shift towards going from the 4 mole side to the 2 mole side, I will steadily lose N2 and lose H2. Those ones here, no doubt, they have increased. I'm going to lose N2. That's going to be in a 1. I'm going to lose H2. That's going to be in a 3 ratio. It never really gets it back down to what it was initially, right? That's still true. It tries to counteract you. And here the NH3, strangely enough, it already had increased just because of the volume change. And this one here will increase even more from there with a ratio of 2. So you can't just memorize, jump up, that means it starts gradually coming downwards. You still have to look what happens afterwards here. Well, as 4 moles shift towards 2 moles, I actually pick up more NH3. Right? There are situations where equilibrium, you may actually have the same number of moles on both sides. In that case, you would say no shift. But in this situation, because I have this difference, every time I shift 4 moles to become 2 moles, I then take 4 particles worth of space. I sort of trade them in for just 2 particles, and that'll end up saving room for me. Again, it's not like particles have a mind of their own. Oh yeah, shifting to that side will end up saving space. You can actually think about this one a little bit more simply. Going in the forward direction, let me just write this down on the side. The forward reaction needs 4 particles to collide, while the reverse reaction only needs 2. Right? So even before I poke the system, which direction was easier? Right? Having 4 particles all happen in the same spot in space, good energy, good geometry, not very likely. 2 particles collision, a lot more likely. Now what I've done here is I've shrunken the container. When you shrink the container, the 2 particle collision doesn't really care. It would have been good anyways, right? It's easy for the energy to run to another energy. But what I've definitely helped is I've helped out the 4 mole side a lot easier. Instead of having such a large room where the 4 moles of gas can actually spread out, now I have a much smaller container here. In a smaller container, the chances of having a 4 particle collision is a little bit quicker. So let's just maybe just draw a quick graph over here. Rate versus time. At first, we're at equilibrium. At first, forward rate is equal to reverse rate. I'm just going to use 2 colors here. Reverse rate and forward rate. All right. So we're at equilibrium, then we can actually do the Chatelier. As you at T1 decide to do the stress, you suddenly shrink the container. Yeah, sure, you would increase, even the 2 particle collision would happen in a smaller container a little bit easier. Both rates would actually increase, but again, what you're going to have is the reverse rate is not going to increase as much as, say, the forward rate. The forward rate really thanks you because you have, well, it was so hard to collide 4 particles all at once. Now I only need 2, now I have 4 particles, still same collision, but I have a lot less room to actually spread out into. And again, we have a situation where the forward rate is bigger than the reverse rate. That implies a shift right. The equilibrium doesn't need a mind of its own. It's able to respond just in terms of rate there. All right. Lastly, let's just finish off here with a catalyst. For a catalyst here, hopefully you remember your definition from the kinetics chapter. A catalyst is a chemical which lowers the activation barrier. It provides an alternate pathway. Maybe at first the energy barrier was too high. That's the EA uncatalyzed. EA uncatalyzed. Maybe I'm going to get from the same start to the same finish. Remember, the delta H is the same, but you notice the EA for the catalyzed pathway is actually a lot lower. It's actually a lot easier of a reaction to get from reactants to products. Now, what I want to just imply here is you'll notice by adding a catalyst, there's actually going to be no change or no shift, no change to the equilibrium, because both forward and reverse reactions are easier. Right? If you look at the forward, right, instead of doing this really big hill, I just have a small hill, but I've lowered that transition energy, transition state here. I've also lowered it for the reverse reaction by the same amount. So in this case here, our general conclusion is just no shift. Now, when I mean no shift, I mean concentration-wise, the lines are just going to keep staying constant. It's as if nothing had happened. But rate-wise, something has happened. If I actually plotted, let's say, rate versus time again, the catalyst has no doubt made the reactions easier. So if I started with forward reaction and reverse reaction, by adding a catalyst, by lowering the activation barrier, I have made the forward rate here higher, but the reverse rate has just sort of increased neck and neck with it here. They're still equal to one another. Whenever the rate's equal, there's going to be no shift in the system. Right? So definitely practice these questions down here. They're going to give you a few equilibrium systems here. They're going to tell you what the stresses are. And all you're going to try to predict is, does it shift left or does it shift right? Okay. Get a lot of practice with this one here, and then we'll go from there tomorrow. Thanks, guys.